PhD.
A PhD in Greece, and after a PhD at he moved straight to New York, or Princeton. And now he's here for this week and next week until Friday next week, right? And he will give a mini course, so 2 lectures today, and the second lecture is Tuesday, isn't it? Same time? I don't remember. It's in the email. So second lecture on Tuesday about black hole superradiance. So I don't really know what it is, but I think I will learn it today.
Okay, yes, like I was saying, I'll be talking about black hole superradiance. And basically introducing what it is and why it's interesting to look at. And kind of the way I'm going to modulate looking at this particular process is through particle physics, which might be unusual perhaps, since we're talking about black holes, but it will make sense in the next hour or 2 or something. Okay, so the first thing you should perhaps know about black hole superradiance is that it's kind of a wave analog of the Penrose process. So, wave analog of Penrose process. I put this in quotation marks because it's not like a one-to-one mapping, but the idea is, just like in the Penrose process, that there is a particular peculiar way of extracting rotational energy.
Sorry. I know Hawking process. What is Penrose process?
What is Penrose process? Okay. So the idea is, and I'll explain some of most of this, but the idea is you have the horizon of a black hole, and then you have an ergo region around this, and then you have some particular way of throwing particles in the ergo region. This is called particle 1. And then in the ergo region, you split up this particle into 2 pieces. One that goes into the black hole, P3, and then one that escapes, P2. And then you can set up this decay inside the region in such a way that the energy E2 is larger than the energy E1, meaning the energy you put in particle 1 is smaller than the energy you get out in particle 2. Okay? So it's kind of the energy here, you're conserving energy in the sense that you're extracting energy from the black hole through this process. And yeah, as you can see in this picture, pictorially it's just a point particle that you throw in and just decays. But the same can happen with waves, like a scalar field. It's not a point particle, but a wave. And in that sense, it's kind of a wave analog because through this black hole superradiance process, you can extract rotational energy from it. Much the same. Okay. Now, why is this useful? It's useful because this superradiance mechanism happens for ultralight fields, or at least the ones from black holes, happens for ultralight fields. So ultralight spin 1 and spin 2 fields, spin 0 and spin 1 fields. So bosonic fields. And what I mean by ultralight is basically masses that are like 10 to the minus 10 electron volts to 10 to the minus 20 electron volts. Okay, so if you think of like the standard model, typical masses there are, order MeV or so, or larger. So clearly this is very, very light in comparison.
Sorry, what is the quantum wavelength correspond to?
Right, so this is like, for 10 to the minus 10, it's order kilometers or so. And then, yeah, 10 to the minus 200. Okay, so this happens for spin 0 and spin 1 fields, and other bosonic fields, although there are some subtleties, around solar mass black holes. So black holes of masses, let's say order 1 solar mass. Okay, by solar mass, just the mass of the sun. Okay, so like a typical stellar mass black hole like we have in the galaxy would be kind of order 1 solar mass, like 10 solar mass or something like this. Okay. So in that sense, it's an astrophysically relevant process because it happens for black holes that we know what we believe exist. But we don't know if this particle exists that would generate such a process. Okay? And so in that sense, it's a way to see, in the black holes that we can see in the galaxy or in the universe, does this process happen? And if this process happens, then these particles or these masses must exist. Okay? So it's basically a probe of Young's model physics.
So if you put it the other way, by not seeing this effect, you can put a bound of model of dark energy with these ultralight scalars, say.
Yeah, basically. Yeah, you can place constraints on spin 0 fields that have these masses. Yeah. And so then you might wonder, okay, well, Nils, you're telling me you can kind of put constraints on masses that we haven't observed anyway. So why would we expect any particle to have these peculiar ultralight masses? And so basically, there are two ways of motivating this from a high energy perspective. The first one is the strong CP problem. Strong CP problem. So basically, this is a quote-unquote problem in QCD, so the strong interaction, where basically the neutron is supposed to have an electric dipole, but we have measured this dipole to very high accuracy, and basically we can say something like the dipole of the neutron is something like some small number. I don't remember the number now off the top of my head, but some small number. I think it's 2 months. But anyway, you can put some bounds on this.
I mean, charge of the electron times Fermi, I guess, is the natural unit.
Yeah, I would say so. But we can put some bounds on this, and basically what this implies is that one particular terminal Lagrangian has to be 0. And there's no natural reason for this terminal Lagrangian to be 0. And so then the way to go around this problem, this fine-tuning problem, is by introducing a new scalar degree of freedom, a new particle, that dynamically drives this term to be 0. Okay? If you're interested in the details, come talk to me afterwards, but it would derail the discussion. But basically, there's some motivation in the standard model itself that a new degree of freedom might be present. Okay?
But that's the effective terms in the Lagrangian.
Yeah, exactly. Yeah.
Just to that particle is the axion?
Yeah, exactly. Right, then of course there's dark matter. We don't know what dark matter is, but people have put proposals forward that it could be something like fuzzy dark matter or ultralight dark matter, which would be a scalar particle of this particular mass, or ish. So something like fuzzy dark matter would be scalar of mass, let's say, tangent minus something like this. Okay? And the last one is a bit more peculiar, and that's basically quantum gravity. So basically in string theory, or at least if you compactify certain spatial dimensions, you can generate towers of particles with different masses. So this might go onto the domain of string axes. So basically, it's just there's some motivation from high energy theory that these particles might exist at low energies. Okay, good. So now we have a rough understanding for what it is, as in it's kind of a way to extract a particular energy from a rotating black hole. And we have some amount of motivation for why it might be actually interesting to look at this beyond just the curiosity of the process itself. Okay. So then, let me ask a question into the room. How many of you are familiar with the Kerr metric? Okay, some yes, some no. Okay. I will summarize the most important aspects of it, just so we all on the same page. So Kerr, let me just write down the metric because it will be important later. Okay. So this is in boiling coordinates. Okay, so here I said G equals 1, just in case you're missing G's and C's, just for keeping it.
Yes, sir, can I ask you a question about this observational part that you said in the beginning? So what is the energy of the particles that would be emitted with these parameters that you said, and how certain can you be that this kind of energy, emission in this energy wouldn't be generated by a process in the standard model, like the accretion disk radiating thermal emissions or?
Right. So there won't. Well, okay. So there won't be any radiation in these particles. It depends on the context, but for the vanilla model, there won't be any radiation from these particles. It will. Well, you will see in a second, but basically, it will generate a cloud of these particles around the black hole, and so there won't be radiation. It will just be sitting there. But it will. The key way of seeing this process is by the spin down of the black hole, and astrophysically, there's basically no mechanism that can drive the spin down on those timescales. This happens on very, very short timescales. And so, yeah, it's quite a smoking gun to distinguish. Yeah. But I'll say more about this in a second. Okay, cool. Right, so what do we need to know about Kerr? So we need to know that there's a time-like killing field.
You forgot to specify the sigma, the delta.
I did, yes, thank you. Right, what are the sigma and delta? Okay, so there's a time-like killing field. But it's time-like only asymptotically. So basically what this means is that it has r to infinity, t mu goes to right, I'm using just in case you're not familiar with this, I'm using the minus plus signature. So negative means time-like, positive means this. Right, we'll be focusing on the regime where the spin parameter is smaller than m, just so basically it's astrophysically relevant and not a singularity. Then there are, basically the horizon sits at r plus, which is equal to m plus m squared minus a squared. Basically you can see this because delta factorizes in the following way. where minus is just minus. Okay.
So in R minus goes to 0 when the spin goes to 0.
Yes.
And R plus goes to the Schwarzschild.
Yes. Yes. Okay. And so I was kind of insistent on the fact that this time-like Killing field exists only asymptotically, or at least asymptotically it's time-like, because it's not time-like everywhere in space-time. In particular, also not everywhere in the exterior of the black hole, which is kind of what matters. In particular, there's the Ergo region. So Ergo region. And basically the Ergo region is defined where the norm of this vector, so mu to mu, is positive. So the asymptotically time-like Killing field becomes space-like outside the horizon, and that's called the Ergo region, which I kind of sketched here already.
That happens also in Schwarzschild, no? It becomes space-like.
No, it becomes null on the horizon.
Yeah, but inside
Inside, yeah, sure. Yeah,
but inside never goes inside.
yeah. Right, so this happens in the exterior of the horizon. And the way to
In the
see,
exterior of R plus or exterior of R minus?
yeah, the exterior of R plus, yes.
Okay.
So the outer horizon is at R plus. So like what you would call the event horizon, that's what is at R plus. Okay. And the way to see that the Ergo region sits outside of this R class is basically by, plugging this in. And so, this is basically just a time component of the metric. So this is basically just minus 1 minus 2 R sigma, which is just this term here. And so the question is, where is this equal to 0? Because we know asymptotically it's negative. Inside the Ergo region is positive, so on the surface of the Ergo region it must be equal to 0. Okay? And so a little bit of algebra will tell you that the Ergo surface sits at what is this? Okay, so in particular, if you look just at the equatorial plane, meaning you set theta to pi over 2, and you set the spin to be nearly extreme, also basically 1, then you'll see that, just write it down, equatorial plane, right? So that is theta to pi over 2. Okay, what you'll see is that the event horizon R plus for A going to M is just M. Okay? But the Ergo surface will go to 2. Okay?
So
there is a lot of physical space in here.
Yes, yes. So
the R plus, sorry, the R plus shouldn't become 1. Why did you say it's just M?
We said it's A to M.
A to M, so this is 0, and it's just M.
But what is the reason for sending A to M?
Oh, it's just an example.
Ah,
Yeah, it's easiest to see there because the numbers are integers of M. Anything in between will be some, basically this expression that's hard to look at. But the main point here is that R plus is smaller than R Ergo surface. Okay, so basically there's a region outside the event horizon where this time-lag killing field turns phase-lag. Okay, now what does this mean? Well, one implication of this is that we can have yeah, so one implication of this is that we can have negative energy states. And the way to see this, yeah, let me not say more about this, it would take too much algebra. But basically you can see that you can see that there are negative energy states because the energy defined like this, because T changes character inside the Euler region, this can change sign as well. So asymptotically it will be positive, but in the Euler region you can have negative energy states. Actually showing this would require some algebra, which I don't want to do. But
you can leave it as an exercise.
Yes, that's the exercise. Show that there's negative energy states in the Euler region. Okay, and yeah, and perhaps one other feature of this is that all observers must co-rotate in the Euler region. So in some sense, the Euler region is an extreme example of frame dragging. So frame dragging is this effect that in a rotating spacetime, even if you throw in an observer like a rock into the spacetime from infinity with zero angular momentum, it will start, precessing around with the angular momentum of the spacetime. Okay.
How does it have to do with the change of signal or of light?
It doesn't. So this will happen like around the Earth as well, and the Earth doesn't have no region. But in this sense, it's an extreme example because all observers, or like all rocks that I throw into the black hole, must co-rotate with the black hole inside the Euler region. Okay? So what that means is that, let's say it's hard to draw. Let's say I throw a rock in such a way that it has negative, very, very large negative angular momentum, meaning that it counter-rotates with the black hole. But by the time it crosses the Euler region, it must co-rotate, even though it was counter-rotating.
The phi direction becomes time.
Yeah.
Instead, the one with the minus in the metric.
Yeah, you're right. Yeah.
So you said for this analysis, you throw the rock straight directly into it, it will be drifted somehow by the black hole.
Right, so this happens in any spacetime. So let me say two words about this. So let's say you have a spacetime. You have a spacetime with angular momentum, spacetime with angular momentum j. Okay, so j is non-zero. So this is true for the Earth. This is true for the Sun. For anything, it doesn't have to be like very extreme. Okay, and basically what you can show is that if I throw in a rock with zero. Okay, so let's introduce a coordinate system. So we have some spherical coordinates in such a way that if I look at the change of the phi direction, the azimuthal direction. So I have my trusty Earth here. The Earth is rotating around that axis, and then the phi coordinates is basically the one that goes around with the rotation. Okay? And then I throw in my rock from infinity. And I say at infinity, phi dot, so the location where the coordinate, the change of the coordinate phi of this rock's its location, the velocity, the azimuthal velocity of this rock is 0 at infinity. Okay? But as it comes towards the Earth, basically what will happen is that this term is proportional to j. Okay? So any spacetime that has non-managing angular momentum will basically induce a non-zero azimuthal velocity as the kind of rock comes. So this is true for any spacetime with angular momentum j, but for a black hole, it's extreme in the sense that it has to co-rotate with the black hole whether or not it started with 0 or some other value. Okay. Good. Good. Now, so that's kind of the key facts about Kerr that are important for this. Now come some other things that are perhaps a little more exciting. So let's understand what happens if we throw in a rock, and this rock has some energy in angular momentum actually. So change of mass and angular momentum of the black hole. Okay? So what happens? And to do this, we need to first define a couple of things. In particular, we need to define what the area of the black hole is. Okay? So, or the area of the event horizon. And so to understand what I actually mean by the area of the event horizon, are all of you familiar with conformal diagrams, Penrose diagrams? Nodding. Okay, good. So let me just quickly draw basically the relevant part of a Penrose diagram. So here's the class here, and then this is the singularity. And then this is the horizon, this guy here. And so you might object if I talk about area, or you might be confused because the horizon itself is kind of it's a three-dimensional hypersurface. It's a null hypersurface. So what does it even mean, area? But what I mean by area is the following. So I define some Cauchy slice. So basically some space-like hypersurface that intersects the horizon. Okay, so we have some intersection here. And basically, at this intersection point here, obviously we're suppressing 2 dimensions. This point actually corresponds to a surface that's 2-dimensional. Okay? Let me call this sigma. Okay? So the dimension of sigma is 2, and more importantly, sigma is a space-like surface. Okay, so then area, the notion of area kind of makes intuitive sense. Okay, so how do we find the area of the horizon? Well, it's actually quite simple, because in Boyer-Lingquist coordinates, the horizon, or this intersection, just sits at t equals constant and r equals constant, or r equals constant. Okay? So basically we can read out the area, or we can compute the area just by looking at the metric. In particular, we just set all the things that are dt and dr to 0, and then we left just the metric describing this surface sigma. Okay? So let me write this down, which is basically just a copy of this. So the metric on sigma, let's call it is just okay? And so then we can compute the area of the horizon by just basically integrating over this. So e2 sigma, well, maybe I have to make that's gamma. Okay?
So this is the metric on the horizon.
Yeah. And so what this will give us, and this is kind of an important metric, so let me put it up here. This will be okay. Where so the way to get this is basically just to observe that the gammas here are just theta phi, basically. And so then you end up just doing a surface integral over a sphere, or topological sphere, and then you get this answer.
We're not recording. Go ahead, I will record the guy.
Okay.
He didn't set up the record.
This also happens in Schwarzschild, right?
What happens in Schwarzschild?
I mean, A0, right? Little a. And you have.
Yeah, the horizon area of Schwarzschild will just be this,
Yes.
where R plus is 2M.
Okay. And what happens with the Penrose diagram then?
It's identical, basically. Okay, so then now we need to, since I was talking about change of mass and spin, we haven't really, so far we've just written down what the area is. But we can recall the following as the area theory. Basically due to Hawking. Which basically states that the change of this area that we find over there must be greater than or equal to 0, assuming some energy conditions that are like satisfied for everything we can think of. Okay? So there's an asterisk that is like assuming energy condition, the null energy conditions specifically. Okay, but basically this is just kind of a caveat, there's no energy condition, and so you should think of this as any matter we can think of satisfies this, and so if you throw something into the black hole, its area can either stay the same or only increase. Okay? And so basically what you can picture this area to be is basically an irreducible mass. As in, like, I give you a black hole, it has some given mass. And there's no way for me to change the area, which basically means there's no way for me to change its mass, or a particular type of mass. And so this basically led Christopher Lewis to find irreducible mass, which is he called it irreducible mass. Irreducible because it can only increase according to this theorem. Okay. Very good. And so basically now, what you can do is you can take this expression here, and basically write it as a function. So basically write A as a function of M and J, where J is just AM. Okay? And so then you can write down an expression for the black hole's mass M in terms of the irreducible mass, or equivalent heat area. So what you'll find is the following. Okay? So basically what this means is that the mass, or equivalent the energy of the black hole, splits into two components. One is the irreducible mass, so that's the energy that you can't access at all, basically because of this condition. But then there's also a secondary term, which is proportional to the angular momentum. Okay, and that you can access in a way that there's nothing that tells you you can't change the angular momentum. Okay, and so
What do you mean when you said that it's not accessible at all? Irreducible.
I meant basically this following relation here, that the irreducible mass can only increase or stay the same because of the area theory. Okay, so it's irreducible, you cannot reduce it. So basically the energy that's contained, the energy equivalent of this mass, you cannot access as an external observer, you can't extract it from the black hole.
Is this mass related to the ADM?
The big M is the ADM mass. Okay, so basically we have this irreducible energy, but then we also have this rotational energy component.
You can see because that's the mass of spatial section of that metric.
Yeah.
That's the capital M. It's the same M that enters the metric. Yeah.
Okay, so what we can also do is basically the following exercise. We can try and understand how much rotational energy is in a black hole. And so basically what we have to do is take this mass and remove the irreducible component from it. And that gives us a rotational energy. Okay? And in particular, just to give you a feel for the numbers, again, in the extremal limit, this will be roughly a third of the total mass, the total energy of the black hole. A third of it is rotational energy. Okay. Okay. But I'm still not at change of mass and momentum. So far, I've only defined certain things. I've defined some angle. I've defined some area. I've defined some irreducible mass based on the area theorem, and then said, okay, we have some irreducible energy and some rotational energy.
But this is just a definition by now, when you call it rotational energy.
Yeah, you can view it as a definition.
Yeah, but you already got the physical consequence, no? That the amount of energy you can extract is most 30% of the mass, the gain mass. That's physical.
But it will not depend on J, this portion?
This will depend on J in general, but so J is equal to AM, right? So in the limit where J goes to M squared,
Okay.
it's this, just to give you a number. It's generally a function of A, but yeah. So for all astrophysically relevant numbers, it would be up to a third, roughly, but not more. Okay, but all of this is just to say that okay, these are just roughly speaking definitions, and we still don't understand what happens if I throw in a rock that has some mass and angular momentum, how the black hole reacts. And so the way to understand how the black hole reacts is basically to see what happens to the area, so the variation of the horizon area as I throw in some stuff. And so basically the variation is just kind of this. Okay? Just a variation. And basically if you plug in this or equivalent to this, you will then find the following expression, which is kind of important. So what you'll find is the following. Where I've defined the following two things. Kappa is equal to
Kappa usually denotes surface gravity.
That's right.
I never understood why it's called surface gravity.
Yeah, I think I'm in the same boat. I mean, there's this. So the way Waltz describes it is this weird concept where you like dangle a mass along a string into the black hole, and it's basically the force you feel pulling on the string, which kind of corresponds to us standing on Earth. There's no string holding us, the floor is pushing us, but the concept is the same. And so if you do that for the black hole, you can then define this as the surface gravity of the horizon. In much the same way that we are standing here experiencing gravity.
So it's a sort of acceleration.
Yeah. I've never really found this very satisfying, to be honest, but I think that's the only definition yeah. I mean, in the quantum picture it will be a temperature, but it's not really a valuable concept, so. Okay, so some of you may recognize this. Especially the first law of black hole thermodynamics, quote unquote. I want to emphasize here that there's no thermodynamics here, this is all just classical gravity. It just happens to look like some thermodynamic law. But this is all just classical stuff.
So R is the entropy, M the energy, and J is the PDV. In the thermodynamic analysis, there would be TdS equal dN minus PDV.
Yeah. Yes. So now we roughly know what happens, right? So if we throw in a rock, and this rock will have some mass delta m, it will have some momentum delta j, then the area will change according to this relation. The area of the black hole will change according to that relation. Okay. And this will be important later because it will tell us how to extract rotational energy from the black hole. How do people feel? Do you guys need a break? 5-minute break?
You should be more tired than us.
I should be more tired. Okay, well, let's keep going. I'm not tired. Okay.
So maybe my question will be so fundamental, but I always have a problem with this. When the rock is going towards the black hole, we're seeing this from outside, very far away. But you won't see it never going inside the black hole. So you never, I mean, we will never see this delta N and delta J because we're outside.
Well, we will not quote unquote see how it crosses the event horizon.
Yes.
But it doesn't mean that the mass is gone, right? The mass is still there.
Okay.
The rock will eventually cross the horizon.
For the local observer.
But also for us in the sense that, okay, it will redshift infinitely, we will not see it anymore, but it will contribute to the total mass of the black hole. Whether it looks like as if it was sitting just outside or not, it will still contribute to the mass.
So then, synodic observer can still feel the effect of gravity in the mass. Its mass, all the gravitational pull of the mass would be felt.
Okay, good. So this is kind of all, just to kind of set the stage for what will be relevant. But so far, only, introduced kind of basic concepts around Kerr and just reminded you of some facts about Kerr. But I haven't really talked about anything that I was introducing initially in the Superradiance process in particle physics. So let's go back there. So the way to understand the Superradiance process is the following. So that's I mentioned this will happen for orbital types of particles, but the simplest way would be a scalar field. So let's just look at the scalar field case. And let's look at the Lagrangian R plus a scalar field. Okay? So R is just the Ricci scalar, and then we have some scalar field phi, some real scalar field phi. Okay, maybe I should change the notations. So mu here we have just a mass term, and then that's just a kinetic term for scalar field. Okay. So the way to understand the Superradiance process. Okay, so the way you might be thinking of a particle I say spin zero fields, is QFT. And in general, you would need QFT to describe exactly what happens around a black hole with a scalar particle like this. Okay? But we're using a trick here, and this trick is kind of borrowed from many-body physics. And so basically what you can show is that many-body system of spin zero particles at the temperature T goes to 0 is basically described by classical field theory. Okay? So well, technically it's the Gross-Peter equation, which is a relativistic limit, a non-relativistic limit of this Lagrangian, but those are just details. Basically, the intuition that is behind this is that if you have, let's say you have a system of 10 scalar bosons, and you cool down the system to like basically 0 temperature, they will all be sitting in the ground state. Okay, so they're all in the same state. And so all you have to do is basically describe what this state, the single state, looks like, and all the particles will just be in this single state. Okay? So the occupation number of the single state can be very, very large because they're bosons. But to describe the single state is actually quite simple because you're just looking at the single state. Okay? So it's kind of the intuition behind it. So the idea is basically now to look at this Lagrangian and try and find this state that all the particles will be in. Okay? Okay, so how to do this? Well, the first thing to do is derive the branes of motion from this Lagrangian. And basically what you'll find is, no surprise, basically the answer intelligence. And then lastly, okay, so these are the equations. So the first line is just the Einstein equation, so that you will get from the Ricci scalar. The T mu you will get from basically the variation of this second piece with respect to the metric. So that will be the stress energy tensor. And then the variation with respect to the scalar field will give you the time coordinate equation, or the massive time coordinate equation. It's kind of important to emphasize that here these are covariant derivatives, not partial derivatives, because we're now in a curved spacetime. And so those won't be partial derivatives anymore. Okay, so in general, this is a set of many PDEs, partial differential equations, and so in general it will be quite difficult to solve all these equations. Okay, but we already know kind of one seemingly trivial solution, but it will be an important solution. And in fact, we have been talking about this solution the entire time, and it's basically the curve metric. Okay, as well as the scalar fields being just trivial. Okay, so in some sense it's a trivial solution. That's an exact solution to this system of equations. But it's important because we can now perturb around this solution. Okay, so we can now say, let's look at the perturbation of this. Okay, some linear perturbation. How does this behave? Okay? And so the way to do this is just regular perturbation theory. Basically just take G, you take phi, you expand it like this, and then you plug it into the equations. And then you expand the equation order by order in epsilon. Okay? And so naturally, what will happen is, this will just be the background equations. So let's call it background which, by construction are satisfied because we're looking at the Kerr metric, which is a solution to the Einstein equations, if the stress energy is zero, which it is if phi is zero. Okay, so then at leading order, it's the first non-trivial thing that comes in. Okay, so we plug this into these sets of equations and then expand to leading order and epsilon. What we'll get is the following. We'll get okay? So basically this h mu is just a linear metric perturbation, a linear kind of gravitational variation. And then the capital phi is the linear variation of phi away from zero, basically. Okay? And what we can see here is quite important in the sense that, well, what we can see, what we notice immediately is basically that the two decouple. Okay? So the first equation only depends on h, and the second equation only depends on phi. But there's no phi that it sits on the right hand side, and there's no h that enters the scalar field equations. Okay, they're completely decoupled, and so we can basically treat them separately as well. Okay.
So why do you use the notation for the version, the first one, and the second one you use?
It's also a box.
It's also a box, right?
Ah, you mean this?
Yes.
Ah, yeah, it's the same thing.
Okay.
And the covariant derivative is with respect to the arbitrary vector?
It's with the background, yeah. Okay, so basically what we can see from this is that we have linear metric perturbations, which just are basically linear metric perturbations on a curved background. Basically, what you can find is that these will just all decay in time. Okay, so all the solutions to this equation will just be decaying in time, and we'll describe like the ring down of a black hole, for instance. Okay, so those have been solved, and we understand them very well. The second equation, on the other hand, is the interesting one, and in fact, it looks identical to this, basically because a linear order they don't couple. Okay, so what we'll have to do is we basically have to solve this equation to try and understand what happens. Well, what's the ground state, or what's the relevant state that all the particles are in. Okay. So to do this, would in general be quite difficult, but we can make use of an approximation that is very, very insightful. So let me do that. Okay, so let's write this out a bit more specifically. We're just interested in this differential operator for now. Basically what we can see is if we just write it out, we'll see terms of the following. Plus other stuff, acting on phi, equal to mu squared. Okay? This is just to say that G is actually G curve, and that in Boyle-Equals coordinates we can just write out all these covariant derivatives in the particular coordinate system that we pick Boyle-Equals coordinates. And then the very first term will be some second time derivative of the fields, and then there will be many, many more terms to come. Okay, so I'm not going to write it all out explicitly because it's going to take a while, but that's kind of the general structure. But what I should write out is the following. Okay, so what I should write out is some truncated form of this. So basically, Okay, so this looks like a, so this is basically just writing out this here, this equation, and then hiding all of the metric factors in these functions that I defined. So the A1, A2, B, C1, C2. And then these here are basically some differential operator in R and theta. And the precise form of those isn't really important. The main point I'm trying to make here is that we can use a separation ansatz, basically because we don't have any cross terms that depend exclusively on R and theta explicitly, right? We only have sums of terms that depend on R and theta. So basically what we can do is we can do a separation ansatz. Separation. Okay. So we can say that this is a function of R, function of theta, phi. Okay. So basically, we're making an ansatz for this single particle or multi-particle state that we're trying to find, and this now needs to solve this particular equation. Okay. And it's a separation that's, yeah, as I said, because we just the dependencies on R and theta are just sum up. Okay. So basically, what we find is two equations which go under the name of basically scalar topology equation. Okay? And let me actually write it out because it's kind of instructive to look at it. First.
Which of those is the Topology equation?
Well, you can kind of think of both of them as typically the first one's called the angular Topology equation, the second the radial, technically speaking, neither of them are quote-unquote the Topology equation. This is usually called the Topology equation because it's just a single one. But yeah, it's basically the two are equivalent. So both of those were the top ones.
Tell me if I'm wrong. I thought that the Topology equation was the one that arises, the first one that you said it is easier to first, or the map for the filtration of the metric. I thought it was that, the Topology equation.
Right, yes, right, yeah. So that's what I'm saying, scalar. So this is the scalar part is important. Because the Topology equation is basically an equation that has some parameter s, right? And this parameter, if you set it to be 2, then you will describe metric perturbations. So h mean. But if you set it to 0, then it's the scalar, and you'll get exactly these equations. Okay. So these look like quite difficult equations to solve, but it turns out there is as I mentioned, there's a limit in which we can make analytic progress, and it will actually be quite interesting to see. So Ricardo asked a question at the very beginning, what the Compton wavelength is of the particle of mass 10⁻⁻⁰ electron volts. And the Compton wavelength, is roughly 100 kilometers or larger than that. And so a black hole has quote-unquote size also, like a solar mass black hole has a size of 40 kilometers. And so the question could be, okay, could we perhaps make progress in the limit where the size of the black hole, or basically just its mass, is much smaller than the Compton wavelength? Let's call it the Compton wavelength L is much larger than the mass of the black hole. Okay? So basically we're looking at a situation where we have our black hole sitting here, and the Compton wavelength compared to the size of the black hole is huge. Okay? So this is the size M, and this is the size L. Okay? So we're looking at a state that is very, very large compared to the black hole. Okay? And this is equivalent to saying that mu M is much smaller. Basically just because the Compton wavelength is 1 over mass. Okay? Now, what happens if we do this? Basically, the first thing that we can see here, if we just focus on the angular equation, is the following. Basically, right, because we make the assumption that A is smaller than M. Basically, what happens in this limit that this term here equals to 0. Okay, so in the angular equation, this term goes to 0. And I forgot to mention that this is this. Okay, so if we set this term to 0, do you recognize this equation? The angular equation without this term.
It's the Jean.
Yeah, basically. It's the polar part of the spherical harmonic equation. Okay, so we already know the solution, S, in this limit. Okay, so basically S goes to P and L, where L arises from number is there. Okay. Okay, great. So we have solved the angular equation. We don't even need to do anything. Now, what about the radial equation? The radial equation is a little bit complicated, but basically what we can find is the following. That again, in this limit, where mu m is much smaller than 1, we will see.
Sorry, I forgot. What is mu?
Mu is the mass of the particle.
The particle.
Yeah. Basically, we'll see that this goes to mu squared 4.
Okay, so you have H bar and G.
Yeah, I said H bar to the 2, 1. Yeah. Right. Basically, the delta will just turn into r squares. So this just turns into r squares in this limit. R squared or r. Yes. This term of this will be. Right. I'm just going to write this out because well, you can verify it in your free time if you feel like it. Cubed. And then we will see that these are not important. Okay? And so then the equation will take this form. And I'm going to ask you again to
You're solving the Schwarzschild case.
Right. So this would be roughly the same around Schwarzschild because all the spin terms dropped out. Yeah. But there will be some things that I will point out in a second. Okay, does anyone recognize the equation?
This is what happens with the hydrogen.
Exactly, it's the hydrogen atom. So the only difference here is that the mu m squared, m mu squared, is the fine structure constant in the hydrogen atom. But other than that, the equation is identical.
Well, it reminds me more of the Zaridi equation. It's
Okay.
the Zaridi equation.
Sure. Yeah. Okay, so basically we know the solution, and we can just write out the solution. And basically what the solution is just MLM. And then we have where this R and ML is just basically the Laguerre polynomials that are I think the solution to the hydrogen atom. And so to just give you a flavor, I'm just going to write out basically the first part, which will be the important part. Okay? And so basically what I did here, I just wrote out some particular state, the 2-1-1 state, to give you some understanding of what this looks like, but basically it's just a hydrogen atom. Okay? So you have some radial dependence, which decays exponentially, where you have the Bohr radius, which is basically 1 over mu squared m. And then this oscillator with some frequency omega. And the frequency omega we can basically get from the hydrogen atom solution as well. And it is 1 minus I didn't define the alpha yet, sorry. U squared. Okay. And there's one more important thing to point out, and that is the sign here. So the sign here is a minus sign. And basically what this means is that these are bound states.
Okay, these are the L equal to 0 solution, I guess.
These are the L equals m equals 1 solutions.
L equal 1, L equal, sorry.
The L equals 1, m equals 1.
Oh, okay.
So the L equals 0, they actually turn out to decay in time.
Okay.
I haven't actually talked about, the only time dependence here sits here, but this is kind of one subtlety with this solution is that in the limit that we took here, we ignored the presence of the black hole completely. The only role the black hole actually played was to have a 1 over r, n over r Newtonian potential here. But what we implicitly did by assuming the hydrogen atom solution R here is that we used regularity boundary conditions at the origin. And that's of course not true in a black hole case, because at r equals 0 we have a horizon, and the horizon is not reflecting, or there is some non-trivial boundary condition on the horizon. And so technically speaking, this is not well, it's an approximate solution, but it misses the part where it depends on time other than the harmonic time dependence here. So in general, this state will decay in time, which is not shown here, because I ignored the flux across the horizon. So this is just to say that the L equals 0 mode will decay in time, whereas the L equals 1 mode will grow in time.
R equals 0 is your horizon or the singularity?
Right, so R equals 0, right, so R equals 0 is pictured as the horizon, but in this solution, the black hole doesn't exist anymore. Okay? In this limit.
You only see the potential of the black hole, basically. The one where
that's
Newtonian potential plus this 1 over r squared.
Yeah.
You don't see the horizon, you don't see the structure of it.
yeah. I mean, there's no spin dependency at all, right? So, like, it's basically just a monopole, the mass turning off the black hole. Okay, but basically what we found is, we found that the particle state is some bound state around the black hole. It has some particular form. And so if you kind of drew a cartoon of this, it would look something like this. Or just basically where phi is large, so this is just a magnitude of phi. Let's say. It's largely the equatorial plane, and then this will oscillate around the black hole with some frequency omega. Okay?
Okay, but then if it oscillates, it must emit.
Yeah, so it will emit gravitational waves.
And also phi. I mean, phi is basically nonsense.
Right, but it will turn out that this state is purely decaying exponentially, even if you include all the relativistic terms. So it will not actually radiate. Of course, if you start with some generic initial data, then it will radiate, but
So, but okay, astrophysically, no, it doesn't, because the mass, okay, it's very light, but still, the compound wave is a kilometer or solar size system. And so, astrophysically, it's a Yukawa potential, so it doesn't.
yeah, sort of.
You said it has some decay.
Yeah, so, right, so this is basically just the spatial dependence, and the time dependence is just harmonic. This is just to kind of illustrate what this state will look like and how you derive it from first principles. It's the leading solution, but it doesn't contain the crucial aspect, which is the presence of the black hole. Okay? So we have completely ignored the black hole, and as I said, implicitly we made the assumption that by using this solution, we've assumed that the solution must be regular at the origin.
Yeah, but in sense, r goes to 0. I mean, phi goes to 0, and when r goes to 0, sure, one can understand it's sort of insensitive what happens r equal to 0.
Yeah,
But it is the potential, because the Newtonian potential you're keeping it.
Right. But yeah, so it's sometimes insensitive, but there will still be more important time dependence. So basically what will happen is, well, what I implicitly assumed here is that at the origin you can't absorb any scalar particles. Okay? But of course you can, because you have a horizon there, so I can just throw scalar particles across the horizon so that it disappear. Okay? So technically speaking, you need to impose radiative, like ingoing boundary conditions at the horizon, which I didn't do here. And then what you will find is, you will find that phi actually goes like e to the I omega t, but omega is no longer just real, but it picks up an imaginary count.
That might be proportional to the mass of the black.
That would be proportional to the mass of the black hole.
But so, how do you arrive to this imaginary part?
Right. So intuitively you can understand it by just this argument I just presented, that you can lose energy into the black hole, okay, just by way of bound conditions. Mathematically, basically what you have to do is you have to keep some of these terms, some of these relativistic terms, and then actually solving these equations becomes more complicated.
So the coefficient multiplying mu squared would become negative then for those cases, in order to have a complex.
No, so this would just turn into the real part. Yeah. So this is the real solution. And imaginary, I have written down because you have to solve the equations, keeping the subunit terms. But yeah, basically when you do this, you'll find that there's this imaginary part. And what will happen is then that, if you write this out, this will be e to the omega RT, e to the I omega RT. And so, if omega I is larger than 0, then the amplitude of the field will grow exponentially. Okay? And it turns out that these states with m larger than 0, or m larger than 0, those states will be exponentially growing. Okay? And so basically what this means is you're building up this cloud around the black hole exponentially quickly. Okay? You extract rotational energy from the black hole, and you deposit this rotational energy in this particle state outside the black hole. Okay, but yeah, I will talk more about this on Tuesday, and I will make more clear exactly how it's related to particle physics.
So about the energy of these particles, could you say anything from this calculation?
Yeah, so you can talk about the frequency, which is basically given here, right? So this is the frequency. And so the frequency is basically the mass plus some small correction, or minus some small correction.
It's a very tiny, right? Because you're assuming that coefficient to be very, very.
Yeah. So the frequency is like 10 to the minus 10 eV or something. But the idea here is that each individual particle is ultralight. Okay. But as I said in the beginning, it's just a single particle state, but you can pump a bunch of particles into that state. In fact, as it turns out, you can show that the amount of particles you can put into the state through this process is 10 to the 80 particles. Okay? So you can fit 10 to the 80 of these ultralight particles into this bound state. And what will happen is that at this point, the cloud will contain a significant fraction of the black hole's mass. Okay, so each particle is very light, but they all combine to some macroscopic mass.
Well, until you suck up all the kinetic energy of the black hole, and then you cannot anymore.
That's right. Yeah, there's an upper bound.
But it doesn't necessarily have to do with the situation that you said, throwing a rock towards the black hole, or does it? This computation. This is just a cloud around the black hole, called scalar particles. It doesn't have to describe the situation of throwing a rock.
No, the throwing a rock was just an example of, an intuitive example of, I put in some energy in momentum, and how would you picture that while you're throwing a rock? Yeah. So the whole derivation I did in the first part about deriving the first law, this will all be important in the sense of how if you include these higher order corrections, how can this cloud actually extract rotational energy from the black hole? And that you can basically derive directly from the first law of thermodynamics.
The claim is that this is rotational energy, what you get?
Yeah.
That's the thing.
Yeah.
The only thing I have a problem to understand, so I understand that you can change the imaginary part for omega from the horizon, but I wouldn't, I mean, you just told us, you have no way shown us that it has the right sign to build up cloud. That it's just a leap of faith at the moment.
Yeah, it's just a leap of faith.
Okay.
There's some intuition behind it that I could
No,
perhaps.
I accept the imaginary part, but the sign,
Right.
we don't know yet.
Right, the sign we don't know yet, but you can imagine the following scenario. So you have some frequency, right? So it oscillates around the black hole with some frequency. But if the spin of the black hole is sufficiently large, you can compare this frequency to basically the black hole's frequency. And if this frequency is smaller than the black hole's frequency, then you can extract it. It's like the same thing as like jumping off some spinning.
Okay, I accept that.
Yeah.
But I guess people, I mean, build actual codes to compute this numerically in a
Yeah.
precise way.
Yeah.
Bypass that approximation.
Yeah. So you can solve this numerically. You can also solve it to a higher order than what I did on the board. To a higher order than what I did on the board. You can keep most of these terms actually, and then do some Nash asymptotic expansion of the solution and get the answer.
But aren't these the things that Pani and guys did?
Yeah.
They have a code, not to do that.
I'm sure they do.
I mean, a public one.
Oh, public, yeah. They definitely have all the frequencies public. I'm not sure if they have a code public. Maybe they do. I don't know.
But that you never used.
No. I wrote it myself. It's actually quite easy to write.
Sorry, just to remind, what is the case with this frequency will explode? What is the case with this only increase?
What is the case? Well, so I'm not sure what you mean by case, but basically it's this solution where this will happen. I haven't shown it, but the leap of faith is that for this state, the n equals m equals 1 state. For this, you will see that the frequency, the imaginary part of the frequency will be positive. And then the amplitude of this state will grow exponentially.
Okay.
But I haven't shown it.
Just trying to create a bridge between the frequency like the black hole. When they are excited, they decay in gravitational waves, and the complex part they are dumped. So the sign is different in this case, right? And I'm just asking because this is like counterintuitive in this case, where
Yeah.
curiosity.
Yeah. So I mean, So for quasi-normal modes, for gravitational quasi-normal modes of the black hole, this will never happen. It will always be negative. Okay, so it'll always be decaying. But in this case, you get this peculiar feature, which is this unstable growth, what you call superradiance and stability. And while one way of picturing it intuitively is basically through this Penrose process. So this is just a scalar wave, but there must be some way that the scalar wave can quote-unquote decay inside the region much the same way that this particle decay in the Penrose process. And if it decayed, and then you get some pulse out, then this pulse will have more energy. Okay? But now you added this mass term here, right? So you have the mu. Basically what this means is that you can generate a bound state. So you have some scalar pulse. You send it to the black hole, it will extract some rotational energy from the black hole. If it were massless, it would just scatter to infinity. But because it's massive, it can be bound to the Newtonian potential. Okay? And so it can keep interacting with the black hole. And the way it keeps interacting is by extracting more and more energy, and it does this exponentially.
Will be a recursive process, right?
Yeah, in some sense. Okay.
Good time to stop. So 90 minutes, like a football match. But without a break. Okay, Last time. I mean, I never had this so clear. So next week it was.
I'm not quite sure yet.
Okay. Right. And what you will be talking Monday?
Probably like testing GR with gravitational waves.
From the in-down, from binder, from Inspire,
Merger.
from Merger.
Inspire merger ring down.
So the three cavitation.
But not so much ring down because the deviations are very small.
No, because I mean, maybe we can talk later. Okay, maybe next week.
Yeah.
No, all these issues people have not identified now if there are overtones or not. I mean, them. I mean, it's a mess, no?
That's why I think testing GR with ring down is, if they can't even agree on GR,
Yes,
imagine
exactly.
just add and modify the GRs.
Which is surprising, no? Because we thought that everything, I mean, after a while, everything should be linear.
I think one thing which would be interesting to look at is a lot of the young GR theories predict that the axial and polar modes go at different frequencies, which is not the case in GR. So if you could somehow measure that from the ring down.
So in the ring down, we build waveforms, we add where do the axial mode enter?
Well, that's the thing. I don't know exactly how you would extract them, but when you derive the spectrum in like just doing perturbation theory, then you have like the axial and the polar modes, and they're the same in GR, so you can just set them equal.
So
in
it's a
beyond
linear edge equivalent.
Yeah, but in beyond GR theories, that's not the case.
So, but the frequencies, but the coefficients that tells how much they're excited, basically nobody knows.
Yeah, sure.
I mean, that's the tricky point now, because even now Alessandra builds, with the Gaussian building the waveforms, but it's all phenomenologically how to fix the pre-coefficient.
It's just calibration coefficients to it now. I mean, it depends on the initial conditions, right? It depends on your.
Sure, no, it depends on what the inspirer takes you to, and then you fix the coefficient, but assuming that the result is superposition, and is a linear superposition of mode, which, is not a theorem, right?
Yes.
The result in a superposition.
In fact, it's not in general, right? Because you have tail terms.
Right. And do people know how to model the tail?
People are working on it right now.
Cool.
But, there's like,
There's
there's Carulo's PhD student, Gregorio Carulo's PhD.
So in Alessandra school?
No, she did it at NBI, right? Yes,
With
so Vito Gregoso.
Marina Stianic.
Maria.
Okay, so these are Vito spin-off.
Yeah. And then,
Okay, so they are more speculative.
yeah.
Alessandra is more speculative.
Yeah, it's true. But it's also, to me, the tail, it's so far down in the link down. I'm not going to measure this. I don't know. It seems very ambitious.
Yeah, okay, but maybe I want to talk to you, maybe you have a better understanding about this, how to present the modes in the down, because I don't like what is being published.
I think, let's talk about it. I think it's worth it.
But yes, all these are real. That just in general.
Yeah, sure.
Do they stop the recording? Stop.
Yeah, so I was just wondering, it's like one thing that I understood is that, when I want to describe no surfaces in my space-time, one way of doing this is just I look at my tuning horizon, so I look at everything vector field, and I look where this vector field is low, and this will define my new surface. In the curve flexible space-time, I have two hidden vector fields. I have the del C and the del phi. And I have like a special combination of them that generates the event horizon, like the outer region. Why just one hidden vector who just the del T being null doesn't generate the null vector?
Yeah, so I guess I'm not quite sure what you mean by this question, because in general, through any space-time point, you can generate the whole surface, right? I can just take some space-time point shoot some light rays out, and the light rays will trace out to your surface.
Like an event horizon.
Well, event horizon is just a special surface. But in general, for any space-time classification, like you can see that in a Penrose type, right? So like if you
Yeah, where is the Earth surface in the
right, well, yeah, so okay, so yeah, so the average surface must be a time-like boundary. So that'll be the average surface. But in general, it's null in the sense that you can define some vector that is null along this, but I can define any vector to be null along any event. Right? So if I pick this event and then I shoot that right here, shoot that right there, this will be null. So there's nothing special about the this surface, the killing vector turning on. There's something special about the killing vector turning on that because but the fact that it is null is not special.
Yeah, I agree. So why is it like if I have a Hooker surface and I have a vector field which is null in its tangent field, how can it still be time?
Oh, you mean the killing vector?
Yeah.
So they're not time-like here. So they're null there. Right?
Yeah.
So like t squared here is time-like. On this surface, t squared equals 0, and then here t squared is 6. So t is asymptotically time-like.
Yeah, but like why is this vector surface then?
Why? It's basically, it's the fact that you have a bunch of angular momentum. So the angular momentum in the space-time has this effect that the time can move into space-time eventually. It doesn't have to happen in a black hole space-time, it can happen in another space-time that doesn't have a horizon where this t turns.
It's all. Okay. Yeah.
What's this example?
No, I think it was okay. And it's for people that they care.
Okay.
I don't know. I think it was